Hi, AP Chemistry. Welcome to Chapter 8. We're going to talk about bonding here for the next couple chapters. So, Chapter 8 and 9, we'll be talking about chemical bonding. Chapter 10, we'll be talking about a couple like quasi bonds that happen in between molecules. So, let's dive in. All right. So when we talk about chemical bonding, when we use this phrase, what we're talking about is a really strong attraction. We indicate it with like a line when we draw things. We actually draw a line between two molecules, but there's not actually anything there. What we're describing is energy. And so that line really represents kind of the directional force that's in between those two things. It's like if you held two magnets close together. There's definitely a force between them, and you could draw a line indicating that they're attracted, even though there's really nothing, no like matter in between the two magnets. That's really what we're talking about when we're talking about a chemical bond. But even though it's not an actual piece of matter, it's still extremely important. Chemical bonding is what determines properties of molecules and reactivity, and it determines those in a really big way. So if you think about something before a chemical reaction happens and then something after a chemical reaction happens, the the properties are actually completely different. So if you think about hydrogen and oxygen combining to form water, we've talked about this one before. So before the reaction occurs, you have two things that are gases. Hydrogen's extremely flammable. Oxygen enables things to combust. They're both colorless unless you condense them, and then oxygen turns out to be a little bit blue. They're both odorless. They're both harmless to breathe in. They get absorbed through certain things. They get blocked by certain things. So, hydrogen and oxygen both have very distinct properties, and we can use those properties to identify whatever gas is present. Present after they chemically bond. So the hydrogen atoms get ripped apart from each other. The oxygen atoms get ripped apart from each other. They reform attached to each other, right? So we have this hydrogen, oxygen, hydrogen molecule. After they rebond like that, they have completely different properties. The properties of water, it's a liquid at STP. It is not flammable. It's also colorless and odorless until you condense it, and then it can reflect back a couple colors. You definitely cannot breathe it in. That's harmful for your lungs. It gets absorbed through different things. It is polar. Oxygen and hydrogen are both nonpolar. So chemical bonding of these molecules actually drastically changes the properties. It gets this whole new set of properties that it didn't have before. And we refer to it as a pure substance. So elements that are bonded together in the same way, if you have like all water molecules, you have a pure substance. Even though you have oxygen atoms and hydrogen atoms present, because they're chemically bonded together, they take on one set of properties and therefore are a pure substance. So chemical bonding is really, really important. It drives a lot of different units that we talk about. And so we're going to dive deeper into what is this idea of a bond. So fair warning, it's going to get really abstract here, very theoretical here. So this is probably our like most abstract and theoretical we will get this year. So hold on to your pants because it's about to get real as far as being abstract goes. Okay, so with that being said, there's not a lot of like practice that we can do with this stuff. And so the practice that you're going to have to take on in this unit is really going to have to be practice kind of like logically piecing these pieces of information together. So you may want to rewrite your notes. You may want to like kind kind of diagram your notes, maybe draw pictures, connect things to pictures, maybe do flowcharts where you can. So the key to this chapter is really getting all those pieces logically lined up so that you can explain. We'll also do a couple things, writing out explanations in sentences. If you can explain it to someone else using words or sentences, that's going to be an indication that you know it more than just being able to kind of repeat the information that I give you. Okay, so your definition of practice kind of needs to switch for these next couple chapters. So let's just keep that in mind as we move forward. All right, there's 3 types of bonds, just like we talked about in chemistry: ionic, covalent, metallic. Ionic bonding is going to be a force that exists because of electrostatic differences. So something positive attached to something negative, that is an electrostatic attraction, and that is what an ionic bond is. Covalent is more attraction based on things like electronegativity. Covalent bonds end in polarity, so you get partial charges. But the stability of a covalent bond, or the driving force behind a covalent bond, really is going to be an attraction between electrons to nuclei, as well as the stability that comes when electron levels or energy levels are filled. So that octet rule of something being very stable when it has 8 electrons in its outermost energy level, that stability, that drive towards the octet rule, that is the driving force between covalent bonds. And then metallic bonds is this like weird type of bonding that is unlike either of the other two. You have this like free flow of electrons through a metallic bond. And really, metallic bonds occur because you have this like sea of electrons that is simultaneously satiating a whole bunch of positive cations at the same time. So we watched this video in chemistry last year where it looked at, I think it was aluminum. So you start with all these aluminum atoms. And what happens to all these aluminum atoms is they all give up their valence electrons. And so what you get, instead of having aluminum atoms, is you get a whole bunch of cations really close together. And then all of those valence electrons, in the case of aluminum, it's 3 valence electrons. All of those valence electrons just become part of this like electron sea. And so those valence electrons can shift and move over all of these cations at the same time. And so they satisfy all of the cations at the same time. And they create this mass that is stabilized with moving electrons at the same time. It's kind of this fascinating thing. And so this ends up being a metallic bond. All right, so we have these 3 types of bonds. You are going to explore these 3 types of bonds a little bit more in the types of bonding POGL. And then you're going to take metallic, this idea of like the metallic bond, and you're going to take it a step further and look at alloys. And so we'll look at one specific kind of application of metallic bonding, and we'll look at what alloys are and how they're formed and kind of the outcomes of that. All right, but before we get into all of this, let's just take a minute to review. So first of all, I want to review electronegativity. When we talked about the periodic table way in the beginning of the year with chapter 7, we reviewed a couple different periodic trends like ionization energy, electronegativity, atomic size, and ionic size. But electronegativity kind of becomes our important one moving forward. The other ones definitely have implications and are good to understand, but electronegativity is the one that we keep coming back to when we talk about bonding. So this would be a good time to pause the video and try to think, what is the trend for electronegativity left to right? What is the trend for electronegativity top to bottom? And why do these trends happen? Okay, so left to right, remember the atom is actually getting smaller left to right. So lithium is going to be bigger than neon, and that occurs because of the nuclear charge. So the Z, or the nuclear charge for lithium, is going to be a 3 plus. The nuclear charge for neon is going to be a 10 plus. Now, we also talked about Z effective and how the core electrons are going to shield that nuclear charge. They're going to block the nuclear charge from the valence electrons. So we can look at Z effective, where we take the nuclear charge minus the shielding electrons equal the effective nuclear charge that valence feels. So lithium's valence electron feels an effective charge of 1. Neon, the Z effective for neon, is going to be the nuclear charge minus shielding electrons, and the Z effective for neon is 8. So those valence electrons for neon feel a much larger nuclear charge. So they're pulled in a lot closer than lithiums are pulled in, and the atom gets smaller. And the attraction of the nucleus for that outermost electron also gets stronger. And that's what electronegativity is. And so electronegativity is going to increase left to right because of that increasing effective nuclear charge. So, like, fluorine has one of the highest electronegativities on the periodic table, but certainly for its own row, because it has such a high nuclear charge compared to others in its row. Okay, left to right, electronegativity is going to decrease. And this also has to do a little bit with atomic size. So hydrogen has 1 energy level. Lithium has 2 energy levels. Sodium has 3 energy levels. So as we add energy levels, the atom gets bigger and bigger and bigger and bigger. And those valence electrons move farther and farther and farther and farther away from the nucleus. And the farther that electron is from the nucleus, the less it's going to feel that nuclear charge. So electronegativity is going to decrease top to bottom because of increasing or additional energy levels. You could also reference atomic size here, but atomic size is also increasing because of those additional energy levels. Okay, so again, let's kind of look at the periodic table as a whole and look at what kind of things have super high electronegativity and what kind of things have super low electronegativity. So if something has a really high electronegativity, it's going to have a really high Z effective, and it's going to be very small, because we see that charge is going to increase electronegativity. Distance is going to decrease electronegativity. So again, we see fluorine here has one of the highest electronegativities of anything on the periodic table. Anything that's going to be on the top is going to be pretty high because it's small, and anything on the right is also going to be pretty small or pretty high electronegativity because of that Z effective. So kind of this area has really high electronegativities. And this has lots of implications. For example, if you look at the halogens, HF is the only weak acid. All the other ones, HCl, HBr, HI, those are all strong acids. Why is hydrofluoric acid the only weak acid? out of the whole group? Well, it's because the bond is so strong because fluorine has super, super high electronegativity. It's a very high electronegativity. It can attract things to itself very strongly. That bond becomes extremely strong between hydrofluoric acid. And therefore, when you put it into water, it doesn't separate very much. It's very stable, being attached to itself. Hydrogen and fluorine are very stable, being attached to each other. They don't really want the additional stabilization that water provides. And so they tend to stay together in water and not separate out very much. Whereas these other things, chlorine, bromine, iodine, they become larger atoms. The attraction, therefore, must occur over a greater distance. And so it's a little stable. Hydrogen versus these halogens are a little stable together. But if you can separate them and surround them by water, they're much, much more stable. And so when you put them in water, they tend to dissociate completely. And that's our definition of a strong acid. When you have hydrogen floating by itself in great quantities and completely dissociated from the anion that it came with, that's going to lead us to a strong acid. So all of this comes back to electronegativity. Now, in addition to electronegativity, we've kind of thrown out a couple terms here like charge and distance. Let's visit that real fast as well. And that brings us to Coulomb's law. Now, we talked about Coulomb's law last year in chemistry. We did a POGIL packet on it. We referred to it again when we covered chapter 7 this year. And again, I gave you that POGIL packet, or I put it on Classroom at least, in the case that you wanted it to refer back to. But Coulomb's law kind of comes front and center. If I were to pick one equation that were the most important equation to our chemistry class, I would choose Coulomb's law. Not because we use it a whole lot or we calculate off of it a whole lot, but because it's a central concept, or it's a driving factor to almost every topic that we talk about in chemistry. Okay, so let's dissect Coulomb's law just a little bit here. It's the variables up top. This first one is a K. The K is just a constant. So you can kind of ignore the K. The K is just that number that makes the equation work. K1 and K2, those are going to be charges. So you can see from this picture, we have a Q1, which is the charge of our first object, and you have a Q2, which is the charge of our second object. So the strength of these charges is going to affect the energy between them. And that's what this Fe is going to be. It's basically the energy that results, the energy of attraction or the energy of repulsion, depending on what the charges is, that results between these first two. So the charge size makes a difference. And we can see this if we look at something like sodium versus magnesium. So sodium is an Na+, magnesium, let me write it on this side. Magnesium is an Mg2+. Okay, so difference in charges here. Sodium's a 1+, magnesium's a 2+. If we're comparing their attraction to chlorine, which is Cl-, I can ask you which one would probably have the stronger bond. And you should be able to tell me that it's magnesium, because this 2+ is going to form a stronger energy of attraction between them than the 1+ would. That's what the Q's on top are going to represent. And then the R on bottom, you may remember, is going to be distance. Distance between them, or the radius of like a perfect circle between them. And so again, this R is going to have an impact on the energy of attraction or the energy of repulsion. And we can look at this too if we compare, let's say we'll compare to chlorine again, and we'll use sodium again. We'll do sodium. Let's look at the periodic table real fast. Let's do francium just for fun. Fr plus. Okay, so they both have a +1 charge, but sodium is going to have 2 energy levels, whereas francium is going to have 7. Okay, so obviously you can see there's a little bit of a difference there. Francium kind of ate my sodium. Let me fix that. Okay, so sodium is going to have 3 energy levels. Francium is going to have 7. Okay, so that chlorine atom, when it bonds to sodium, can get a lot closer to sodium than it can to francium. So the NaCl bond between those two is going to be a lot stronger than the FrCl bond between these bottom two. And not only does distance make a difference, so with increasing distance, our denominator gets bigger, therefore our energy gets smaller. But notice that it's squared also. So it actually has more of an effect. If you were to double a charge, go from, Q2 being 1 to Q2 being 2, that would probably double your energy of attraction. Well, if you go from an R of 1 to an R of 2, it's going to quadruple your energy of attraction. So distance has an effect, and it has an exponential effect when compared to Q. Okay, so Coulomb's law, these two ideas of distance and charge are really going to drive a lot in bonding. They drive a lot in periodic trends. They drive a lot in intermolecular forces. And all of this has an effect on all of our application, like thermodynamics and the energy of a lattice and the heat of a reaction and the disorder that occurs and the equilibrium that we find and the reactions between acids and bases and the how fast a reaction occurs. Like all of that gets tied back to Coulomb's law. And so, like I said, we don't really calculate a whole lot using Coulomb's law, but it's such a central idea to chemistry. It's definitely a law you should use. And if you can reference it in a free response question, you are probably doing well by doing that. Okay, so we reviewed electronegativity. We reviewed Coulomb's law. I want to review Lewis symbols. So remember, Lewis symbols, super simple. They're going to show valence electrons only. So if we were to look at sodium, the sodium ion, it has a lot of electrons. But in the Lewis symbol for sodium, the only electron that's going to get represented is actually the valence electron. So you ignore all the core electrons and you just use the valence electrons in your Lewis symbol because valence electrons are the bonding electrons. The core electrons aren't really used in bonding at all. And so when we take a look at a couple different models for bonding, we really want to focus in on those valence electrons. And the Lewis symbols are going to take those valence electrons and they're going to show them in a way around the element symbol that supports bonding. So remember when electrons fill energy levels like 1s, 2s, 2p, remember the electrons are going to fill one at a time, and they're going to pair when they have to. They fill one at a time, they pair when they have to. It becomes really apparent with the 2p electrons because the next 3 electrons are actually going to go into different suborbitals until you get enough electrons where the electrons are forced to pair. And so when we draw electrons around our symbols, we want to kind of reflect this idea that electrons are going to spread out until they are forced to pair. So lithium has 3 electrons, but 2 of them are core, and so we're going to show 1 electron here for lithium. Beryllium also has 2 electrons, so the 3rd and the 4th electron get displayed. And notice that I'm separating the electrons as if they are on separate sides of a box, right? Boron has 5 electrons total, 2 are core, so the 3rd, the 4th, and the 5th electron get spread out around the symbol of boron. So you're going to draw them as if they exist around a box. You're going to spread them out if possible. And then you're going to pair them if it's not possible to spread them out. Let me show you an example of that. So carbon has 6 electrons total, 2 are core. We're going to put 4 around carbon, 1, 2, 3, 4. Nitrogen has 7, 2 are core, so it gets 5. So I'm going to do 1, 2, 3, 4. Now the 5th one's going to pair. Okay, so don't spread your electrons out around the symbols evenly. Definitely pair them. A couple other reminders. The first energy level can hold 2 electrons. Remember, that's the 1s orbital. The second energy level can hold 8 electrons. Remember, that's the 2s and 2p orbitals. There's 1 2s, and then there's 3 2p orbitals, 2px, 2py, 2pz. And then after that, the energy levels start to get additional shapes or suborbitals. Like the 3rd one is going to have the 2s, or sorry, not 2s. The 3s orbital, the 3p's, and then we'll get 5 3Ds. But remember that the Ds and Fs don't fill until the next energy down has already filled S and P. So 4, energy level 4, is going to fill 4S and 4P. And then electrons will go back into filling the 3D orbitals. So the valence electrons really for any shell are only ever the S and P orbitals. And so valence electrons, the maximum you can ever have is 8, because the 9th electron is actually going to go into the next energy level. And then all of a sudden, your S, Ps, and Ds aren't valence anymore. They're core electrons. Okay, so just a couple of reminders there. Let's finish these valence electrons. Now would be a good time to pause the video. Try to draw the Lewis symbols for oxygen, fluorine, and neon, and then come back to see if yours lines up with mine. Okay, so there's what oxygen, fluorine, and neon are going to look like. Definitely reach out if you have questions. Let's talk about those questions in class. I know this is review from last year, but it's a pretty fundamental skill to be able to draw the Lewis symbols. So if you have questions on these, let's deal with the questions now before we kind of build on top of these layers and then throw like additional confusion in there. So let me know if you have any questions on Lewis symbols. All right, and then the octet rule. So we kind of referenced this already today, but let's go over the octet rule one more time. So atoms are going to gain, lose, or share electrons until they're surrounded by 8 valence electrons. Basically, they're going to gain, lose, or share electrons until they have the same number of electrons as noble gases. Noble gases fill their energy levels, and they achieve this like mighty stability where they're very, very stable on their own, we actually have a hard time forcing them to bond under very specific and extreme lab circumstances because they're so happy by themselves. And so all these other elements on the periodic table, they're going to gain, lose, or share electrons until they also have either a full valence shell or an empty valence shell. So let's look at a couple of these. Let's look at fluorine and neon. So we'll compare them to neon. We're going to look at fluorine and we're going to look at sodium. Okay, so fluorine is going to have 2 energy levels. It's going to have 9 total electrons, but fluorine is very close to having 8 on the outside, so it just needs 1 more electron here, which it's going to usually gain from another element, bonding with that element, and all of a sudden fluorine has the same amount of electrons in its outer ring as neon. Neon has 10 total. Notice its outer energy level is full. And so fluorine is going to form the F minus ion because it's gained an electron, and now it has a noble gas configuration that matches neon. If we look at sodium, okay, sodium's in the next energy level down. It's actually over here on the periodic table, but I'm going to draw it below neon just for comparison's sake. So 2 in the first, 8 in the second. Oh, that's not neon. Let me get that symbol right. This is sodium. And then it has 1 in the outermost electron. And okay, so sodium is also very close to neon's configuration. It just has 1 more electron. So sodium is going to typically lose that, probably to an element like fluorine, right? And after it has lost that 1 electron, sodium is now an A plus. It has lost 1 negative, so now it's positive. And it also has a similar electron structure to that of neon. So this is what elements do. They either gain electrons or lose electrons. They can gain or lose 1 electron or 2 or 3 or as many as they need to in order to either fill their outermost energy level or empty it completely. And that is what we call an octet. So an octet just means there's 8 electrons on the outermost energy level. The only 2 elements that break the octet rule are hydrogen and helium, because hydrogen and helium have only 1 energy level, and that 1 energy level is the 1s energy level, which can only hold 2 electrons. And so hydrogen and helium have a duet rule. Everything else has an octet rule where the S's and P subshells are completely filled. Now, like most of our models in chemistry, where we fallible humans are trying to describe usually perfect nature, are the models that we build to describe and to predict are going to have exceptions. Again, there's many exceptions to the octet rule, but it's a really good framework for talking about bonding. It basically covers 99% of bonding circumstances that we're going to encounter. Actually, 100% that we're going to encounter, but 99% that you may encounter outside of this class. So it's a pretty good framework. Okay, ionic bonding. So we're going to start with basics that you've probably heard before and kind of build on them. So here's your abstract thought coming. So here we go. Okay, so when we're talking about ionic bonding, we're talking about cations and anions. Remember, cations have a positive charge, anions have a negative charge. Cations and anions that are attracted to each other. And again, that positive and negative attraction or repulsion is called an electrostatic attraction or electrostatic force. Notice that already sodium has lost that electron and obtained noble gas configuration. Chlorine also has gained that electron and obtained noble gas configuration. Now, something interesting to note here as they write out the symbols, notice that if something loses an electron and is now positive, you just draw it without any dots and you draw it with the charge. On the other hand, if something gains electrons, you draw all the dots plus brackets and a charge. So if magnesium, which starts like this, loses its 2 electrons, you're going to draw magnesium with no valence electrons and a 2 plus charge. On the other hand, if you're looking at something like oxygen, which is going to gain 2 electrons, you're going to draw the oxide ions Lewis dot diagram with all of the electrons plus brackets plus a charge. So that's what they've drawn here with sodium and chloride. Now you can see that if you look at the enthalpy of formation of this, it's extremely exothermic. So it's going to drive forward pretty strongly and release a lot of heat in the process. And this is going to happen anytime you get 2 elements together that have very different electronegatives. When they differ greatly in their attraction for electrons, that is another way of describing electronegativity. And actually, when we taught you this concept of ionic bonding in chemistry, what we taught you to do was look up the electronegativities and subtract them. And then that difference in electronegativities would actually sort the atoms for you into the different types of bonding. So this difference in electronegativity really is the driving force in bonding. Anytime something loses an electron, it's always going to be endothermic. You can think that energy has to be put in to remove the electron from the system. Anytime something gains an electron, which is what we see when we look at nonmetals, it's almost always exothermic. Usually the system is going to become more stable by that gain of electrons. And so it's going to give off that extra energy, that extra potential energy as heat usually. And that's an exothermic process. So usually exothermic. Whenever you look at the enthalpy of formation for ionic compounds, the enthalpy of formation is always going to be pretty negative. Okay, before we look at bond energy, I just want to show you one more thing. Ionic compounds and covalent compounds and metallic compounds, not only do they have very different descriptions of their bonding, but that bonding results in very different structures. So I want to show you some of those structures. All right, so you can see when we form an ionic compound, we write ionic compounds as NaCl, right? It looks like NaCl goes to blah, blah, blah. It looks like we have 1 sodium and 1 chlorine bonded together, but that's actually not accurate. Whenever you have ionic compounds that form, they form what's called a lattice. And you can see a couple different examples of lattices here. We have a space-filling lattice here. We have a stick and ball lattice here. You can see the different types of lattices, but they're basically highly structured compounds. So if you look at this one over on the side, look at this little blue thing right here. Yes, it is connected to one chlorine, right? One chlorine is connected to another sodium. And we can see that ratio over and over and over and over and over and over and over again, right? We always see that ratio of one sodium to one chloride. However, notice that one sodium or that one chlorine, here, we'll look at this chlorine here in the middle. Look, it is, actually, better example, wait for it. Look at this sodium in the middle here. Look how many different things it's connected to. 1, 2, 3, 4, 5, 6. It's connected to 6 different chlorines. So yes, there is a ratio of 1 to 1 inside this compound, inside this structure, this lattice or this crystal, right? But it's not just connected to one other ion. It's connected to many, many different types of ions. And if you kind of browse through chapter 8, the section that we're really skipping is the type of solids that form. Let me see if I can pull this up real fast. Here we go. There's so many different types of crystal structures that form. So if you go into geology, you will definitely look at this like crystal structure formation. But there's a bunch of different types of these solids that form. And it's just based on a lot of different factors within the ions themselves, charge and size and electronegativity and ionization energy. All of these things are going to come together to describe the types of solids that form. Now, it is outside of our scope and sequence to talk about the different types of solids that form. So you actually don't have to know the different types of solids that form. You don't have to be able to deal with them. You don't have to be able to calculate them. If you continue on with chemistry, and especially you go into like the geology side of it, you will walk through this, but you actually don't have to walk through it in our class. So you read through it once, you know it exists. If you need to reference back to it, you can, but we're actually going to skip all of these questions in the back of the book. The one thing I do want to point out, though, that is definitely within our sequence is ionic bond energies. Lattice energies, also known as lattice enthalpies. So this is a throwback to the unit that we just did on thermodynamics, and it talks about the energy changes that occur when lattices are either formed or broken down. Now, we did talk about energy diagrams here, and you can see an energy diagram for the formation of sodium and chloride, the sodium chloride salt. Again, we're operating off of these two principles that a loss of electron is always endothermic, a gain of electron is always exothermic. And so you can see that in this diagram. Here we have sodium and chloride, and then the sodium has been ionized here. Nothing has happened to the chlorine. And that has required an input of energy, an input of quite a bit of energy, right? And then the chlorine being split and ionized has actually released energy because the chlorine has gained an electron. So that's usually exothermic. But notice that there's still this net change of 147 kilojoules per mole. So at this point in time, when we take elemental sodium and chlorine, and we ionize both of them, that is an endothermic process. But the formation of NaCl salt is actually extremely exothermic. And the reason for that is, if this is my energy diagram, okay, here's my first 3 lines, right? Well, going from ionized sodium and chlorine to a place where those two are bonded together is extremely exothermic. And so this energy of those two bonding together is going to just dwarf the rest of this energy diagram because it's so exothermic. And that is what you're going to look at when you explore that lattice energy POGL. So we have a whole bunch of exploring to do in front of us. I want you to explore bond types a little bit. I want you to explore alloys once you kind of get through the general principles of bond types and categorizing metals. And then I want you to explore lattice energies. So we have a lot of exploring to do. Remember, exploring is better if we do it within conversation. So if possible, do your exploring, your process-oriented exploring with another person. Let me know if you have questions. We'll come back together and talk through all of this. So let me know if you have questions. I will see you in class.